Hello everybody, welcome to our first lecture of ATM 5, our changing atmosphere. In this class, we'll be learning about the Earth system and how it is being affected by climate change. I'm Professor Paul Ulrich, and I will be your instructor for this class. In this fall 2020 offering of this class, we will be having synchronous lectures on Monday and Wednesday from 1:10 p.m. to 2 p.m., in addition to these asynchronous lectures which will be posted online. There are 3 discussion sections from the class. Please check to make sure which discussion section you're associated with. The GE credits for this class are Science and Engineering, SE, QL, SL, and VL. Here I am in the bottom left. Here's my email address in case you need to contact me. I'll be holding office hours on Thursdays from 2 p.m. to 3 p.m. or by appointment. Don't hesitate to shoot me an email. And you can find me on the web at climate.ucdavis.edu. We have 4 teaching assistants for this class: Raymond Cicado, Xavier Noguera, Helene Barris, and Min Mung Tang. Their office hours are listed on this slide in case you need reference, or you can find this information on the Canvas site for this class. The overall goal for this class is an analysis of global climate change. We're going to be focusing on scientific methods and principles that are used to observe and analyze the physical processes underlying the climate system, and we're going to apply these principles to emphasize seasonal, regional, and global climates. In order to contrast this against other climate change classes you may have taken or may be interested in taking, this class focuses heavily on the science of climate change. That is, we're going to focus on the physical system and understand how humans can influence that physical system and the consequences. The course format is 2 lectures per week. We're going to have both asynchronous and synchronous lectures. Both the asynchronous and synchronous lectures will be covering the same topics. And these lectures will emphasize concepts, relevant principles, and applications of interpretive techniques. There's also 1 discussion per week, again depending on your section, for discussing complementary material, readings, and current topics related to climate change. The overall grade will be computed as 20% from online quizzes. There will be 1 quiz associated with every lecture of the class. 40% assignments. There are going to be 8 assignments total for the class, and they'll be weighted equally. And a 40% take-home final exam, of which you'll have a few days in order to complete the final exam material, and it will be cumulative over all the content of the class. The recommended textbook for this class is Donald Aaron's book, Meteorology Today, currently in its 12th edition. This book, I would say, is an excellent reference for understanding the Earth system. Note that we do not follow this book particularly closely throughout this class. Most of the material is fairly customized for this class, but nonetheless, if you are interested in having a second source for understanding the course material, then I'd recommend getting yourself a copy. Other references, in case you want to learn more about climate change, are also listed here. If you're interested in a pocket guidebook about climate change, I recommend Carrie Emanuel's book, What We Know About Climate Change, with a new edition having been released recently in 2018. This, I'd say, is a handy primer on the course content, and it can be read completely in only a couple hours. It's essentially just a pocket book on everything we know related to climate change. It's a bit more than $10 on Amazon, so if you want to get spun up quickly on the course material, this is a good place to look. The science of climate change at this point is very well understood, and most of what we know has been accumulated by the Intergovernmental Panel on Climate Change. Its assessment reports, which are compiled every 5 to 7 years, are a wealth of information related to climate change. Some of it can be pretty intense, I should say. So you can always delve in and examine some of the easier material first before taking on some of the more challenging concepts. The most recent published report from the IPCC is the 5th assessment report, or colloquially called the AR5, which was published between 2013 and 2014. Now, it is a little bit dated relative to 2020, but all of the science that from 2013 and 2014 still holds today. We've learned a little bit more about climate change and some of the more nuanced aspects of how it's affecting the Earth system, but for everything you need to know in this class, the 5th assessment report provides you with what you need to know. The next assessment report, the AR6, was not out quite in time for this class. We anticipate it will be published in the beginning of 2021 through the beginning of 2022. Nonetheless, the AR5 and earlier reports are going to be a handy reference for learning this material, and some of the readings that we'll have in this class will actually be drawn from these assessment reports. Couple more references for those interested. Marshall and Plum's 2007 book, Atmosphere, Ocean, and Climate Dynamics, is an excellent reference on how the Earth system operates, and is actually the textbook for my graduate level class on climate dynamics. If you aren't afraid of mathematics and want a deeper understanding of how energy and moisture move around the Earth, you can grab a copy of this text as well. And you can even follow along with my YouTube lectures on climate dynamics, which are on my YouTube channel, which I'll bring up momentarily. Finally, in terms of physical reference books, we have David Neelan's 2011 book, Climate Change and Climate Modeling. This is an excellent source of information on how we've used climate models to delve into the science of climate change. As a climate modeler myself, I'm of course a little bit biased towards understanding and employing climate models, and so I may bring them up here and there throughout the course. This book, however, I would say is a great reference in case you're interested in learning more beyond what we teach in this class, in particular about how what techniques scientists use in order to understand the climate system. As mentioned earlier, all of my videos are going to be posted online to my YouTube channel, Introduction to Atmospheric Dynamics, which you can find by just Googling Introduction to Atmospheric Dynamics, or you can follow this tiny URL link shown here. The channel includes videos not only from this class, but also includes videos from when I taught atmospheric dynamics, which is ATM 121A and 121B, as well as climate dynamics, which is atmospheric science 241. Feel free to check it out if you're interested in learning more about atmospheric science or just really like hearing me talk about things. All right, so I always like to kick off this course with a look at how climate change has shown up in the news. One of the primary references to track the science of climate change is actually the NOAA State of the Climate report, which comes out every month. The most recent report that I'm working from here is the September report, which covers material all the way through the end of August. Since NOAA has access to a wide array of different observing stations and a copious data set of past climate data, it provides an expert look at how the global climate system has been changing. In 2020, it's been an interesting year to say the least. We've suffered pandemics, politics, and extreme weather. As climate change continues to intensify, we are also continuing to experience anomalously warm weather all over the globe. This is a natural consequence of climate change and one that we'll be studying in detail over the next few weeks. Every month, basically, that for the past several years, we seem to be experiencing some sort of new record being broken. Looking back over the summer of 2020 in particular, NOAA reports that the Northern Hemisphere has actually experienced the warmest summer on record. And actually here in California, we've experienced the warmest August on record. If we look closely at this graph, we can actually see that the last 6 years have also been the warmest 6 years on record for the Northern Hemisphere. And this is no coincidence. Just to get that out of the way, this can be directly attributed to human activity and human emission of greenhouse gases to the atmosphere, which causes near-surface warming and consequently anomalously high temperatures. North America has also experienced its warmest August on record at about 1.52 degrees Celsius or 2.74 degrees Fahrenheit above average, and globally, this was the third warmest summer on record, a record currently held by 2016, which was an anomalously strong El Nino year. Later in the class, we'll talk about how instances of climate variability, such as the El Nino event, also influence these temperature records, as well as the global temperature climatology. Summertime temperature departures from the historical averages have basically showed that effectively everywhere on the globe is experiencing temperatures that are above average. Record warm conditions were observed in many places, including the western equatorial Pacific, which you can see on the right-hand side of this particular map, as well here in the southwestern U.S. As we'll learn from this class, these rising near-surface temperatures are a direct consequence of how we've been modifying the Earth's atmosphere. And this is not particularly anomalous of what we should be experiencing in the years to come. Essentially, if we look at any month going forward, what we will see is continued records being broken of warmer and warmer temperatures. On the extreme weather front, 2020 has also been a record-setting hurricane season for those of you paying attention. And it's only September. The hurricane season will continue for the next couple months and likely result in even more records being broken. For only the second time on record, we've had 5 simultaneous tropical cyclones active in the Atlantic, This occurred on September 14th. And for the second time in history, the last time was 2005, we have actually exhausted the standard names for Atlantic storms. So far in the year, we've seen Hurricane Alpha as well as Hurricane Beta show up in the Atlantic. We're going to continue using the Greek alphabet in order to name these storms, and hopefully not exhaust the Greek alphabet as well. 2020 has already tied 1916 for record number of U.S. landfalls, and as I saw earlier today, there's only the west coast of Florida that has actually not been under a hurricane watch so far this year. The amount of damage associated with this hurricane season has been extensive and dramatic. Hurricane Laura is estimated to have cost from $4 billion to $12 billion in total damages to Louisiana and Texas. Further, extensive flooding that has been experienced from Hurricane Sally is estimated to have cost from $8 billion to $10 billion. As we'll learn later in the class, climate change has an indirect impact on tropical cyclones. Warmer ocean temperatures provide more fuel for these hurricanes, leading to more intense storms. Warmer air holds more moisture, leading to heavier precipitation and more extensive flooding. Sea level rise, caused by melting land ice and thermal expansion of the ocean waters, is intensifying storm surge. However, contrary to what we've seen in 2020, our climate models also project a decrease in the total number of tropical storms, as more intense systems are more disruptive to storms that follow in their wake. So even though the tropical cyclone season tends to be highly variable, it seems that this year has been a particular anomaly, but that anomaly is still in the context of climate change. Here in California, we've also experienced a dramatic wildfire season that is one of the worst on record for modern civilization. 5 of the 20 largest wildfires in California history were part of this 2020 wildfire season. And this is the largest recorded wildfire season in California's history. The effects, again, have been dramatic to us in the U.S. West. As of September 22nd, 2020, a total of 7,982 fires have burned about 3.6 million acres, or 1.5 million hectares, or more than 3.7% of California's approximately 100 million acres of land. If you want to learn more about these fires, you can check it out on the CAL FIRE website link provided here. These fires have been exacerbated by an anomalously dry spring season and a heat wave during the summer that left most of the state primed for intense fires. Studies have focused on how these fires are changing, and in the next lecture, we'll talk a little bit about how wildfires are expected to change in response to climate change. Later in this class, we'll also be learning more about how climate change is causing the landscape of Northern California to transition from the temperate forests to shrublands more commonly associated with Southern California. So at the beginning of each lecture for this class, I will generally provide a set of definitions that you are expected to learn. This is going to be some of the material that will be tested on both the assignments as well as the final exams for the class. In addition, I'll provide a set of questions that we are trying to answer in this particular lecture. So in this case, we're going to define climate and weather, and we're going to answer the questions: where on Earth are temperatures highest, lowest? Where on Earth is precipitation highest and lowest? And what are the 5 components of the Earth system? All right, let's get started by defining climate and contrasting it against weather. So climate is the pattern of variation in temperature, humidity, atmospheric pressure, wind, precipitation, atmosphere particle count, and other meteorological variables in a given region over long periods. I emphasize that these last 6 words are particularly important for defining climate. That is, you have to define a location for which you're talking about the climate. As well, climate must occur over a long period of time. Here we're talking about the statistics of weather, not specific weather events. Thus, climate can be contrasted to weather, which is the present condition of these variables over short periods. So this is different than the climate signal, which is over a long period of time. Often you have strong variation in things like daily temperatures. The daily temperatures themselves, though, are individual weather signals, but they exist on top of a long-term history of average conditions known as the climate. As the climate warms, on average, what we tend to see is more instances of warmer weather events as well. But again, those occur on this backdrop of the average climate. Climate also describes the variability of weather events, namely things like the probability of a major rainfall event occurring in July in San Francisco, or variations in temperature that typically occur in January in Chicago. In some sense, You can again think of climate as the statistics of weather. Weather, on the other hand, is the state of the atmosphere at a place and time with regards to these meteorological variables. So if a snowfall occurs, that's a weather event. If a tornado occurs, that's a weather event. If you have a lightning storm, that is a weather event. That is a short time scale event that affects a particular location or region. Nice weather also is a weather event. That is, it's the state and conditions of the meteorological variables at a particular point in time. When you average all those weather events over time, that gives you the climatology of the region. Things like the probability of a snowfall or the probability of a tornado or the probability of nice weather are all climatological variables. There's a nice way in order to construct this idea, climate versus weather. Weather is basically what you get. It's what you're wearing today. What you're wearing today is in response to the weather of the day. Climate, on the other hand, is what you have in your closet. You have all sorts of clothes in your closet to prepare you for the types of weather events that could occur on each day where you live. Consequently, you have a large statistical sample, many different days of weather, all stored within your climate closet. In order to understand what people have in their various closets worldwide, we typically break the world up into what are known as climate zones. These climate zones are regions that of relatively similar or homogeneous climate. It's common to classify these zones by what is known as a Köppen climate classification, such as the one shown here. The climate of the world is affected primarily by temperature and precipitation. Polar regions are cold, equatorial regions are hot. Precipitation is generally higher at the equator and varies depending on the location elsewhere. Depending on that combination of temperature and precipitation, we can divide the world up into tropical, dry, moderate, continental, and polar climate zones, and then subdivide those further based on the average climatology in each of those regions. In order to understand what gives rise to these climate zones, we must then study the temperature and precipitation of the world. As mentioned before, temperature has a pretty basic variation over the Earth's surface. The warmest temperatures are found near the equator, or the middle of this plot. The coolest temperatures are found towards the poles, or the top and bottom of this plot. Also, as you tend to go to higher elevations, you also tend to find cooler temperatures overall. Temperature also varies throughout the year depending on where the Earth is in its orbit. In December and January, the tilt of the Earth causes the southern hemisphere to be facing more directly at the sun, consequently driving up temperatures in the southern hemisphere. As we move forward in the year, we have the sun now moving from overhead in the southern hemisphere to being overhead in the northern hemisphere. Consequently, this region of maximum temperatures also moves with the sun. During this season, we see warmer temperatures in the northern hemisphere and cooler temperatures in the southern hemisphere. In particular, you see here Antarctica becomes very cold in this northern hemisphere summer season. Temperatures are generally warmest around the equator, although that point of maximum temperature does tend to follow the sun north and south. Temperatures are also affected by differences between ocean and land. It takes much more energy to warm up ocean water than it does to warm up land. It's also much easier for the land surface to lose its energy through radiation and evaporation. As a consequence, ocean temperatures tend to be much more stable than over land, where we see much more dramatic shifts in temperature between seasons. This is also one of the reasons why coastal regions typically tend to be much more mild and have a weaker temperature variation than more inland regions. The ocean is a natural regulator of temperatures and thus provides those coastal regions with modulation of their temperatures. Finally, temperatures are also affected by dynamical patterns of the Earth system. The Gulf Stream, which goes from the Gulf of Mexico northeast through the Atlantic Ocean, is responsible for transporting warm water across the Atlantic. It's also responsible for pushing up temperatures in Europe. Because of this pattern, we see warmer waters in Europe at the same latitudes that we see them in North America. Wintertime temperatures in Goose Bay, Newfoundland are around minus 18 degrees Celsius. In Dublin, Ireland, which is at approximately the same latitude, wintertime temperatures are rarely below freezing. That's about here for Goose Bay, Newfoundland, and about here for Dublin, Ireland. In general, because of these weather and oceanic patterns, the west coast of these continents tends to be significantly warmer than their east coasts. Looking at precipitation, we see that the wettest regions of the world are around the equator. This is because of convergence and lifting of moist air in a region known as the Intertropical Convergence Zone, or simply the ITCZ. This is also where we'll find most of the rainforests of the world. This wet band tends to follow the sun north and south with the seasons as well, as we will see. As the sun moves into the northern hemisphere, that region of intense precipitation moves along with it. And as the sun moves back to the southern hemisphere, in December, we have that the wetter regions also move to the southern hemisphere. To the north and south of the ITCZ are the subtropical latitudes, where descending air from the ITCZ naturally suppresses precipitation and drives drier conditions. This is also where we'll find the deserts of the world, including the Sahara in the northern hemisphere, as well as the Kalahari and the Great Australian Desert in the south. Going again poleward, we enter the mid-latitudinal regions here. In the mid-latitudes, there's strong longitudinal variation in precipitation amounts. As you can see along the western coast of the United States, this is typically very wet in the winter season. Then we have drier conditions through the mountains, as well as more modulated conditions in the eastern US. Similarly, in Europe and Asia, we see wetter conditions along the western coast of Europe and drier conditions as you go farther inland in Asia. California, as we know, is very wet in the wintertime and dry in the summertime. The east coast of the US, on the other hand, where precipitation mainly comes in the form of transport from the Gulf of Mexico over land, tends to have a relatively same amount of precipitation regardless of what time of year it is. If we go farther north still, we enter the polar regions. And this is where we again find incredibly dry conditions, because the cold air of these regions cannot hold on to atmospheric moisture, and consequently that moisture cannot be used to generate precipitation. The driest regions of the world can actually be found in these polar regions, with the driest region of the world actually found in what is known as the dry valleys of Antarctica, where the average precipitation is essentially zero. Even for the large deserts of the world, it's very rare to find locations where you have absolutely zero precipitation. Combining these two plots and averaging across longitudes, we obtain the chart shown here, where you have the southern hemisphere on the left of the plot and the northern hemisphere on the right of the plot. The red line shows the temperature variation as a function of latitude, and the blue line shows precipitation variation as a function of latitude. As in the previous discussion, we've broken up the Earth by latitude into a variety of regions, including the equatorial zone, the subtropics, the mid-latitudes, the subpolar region, and the polar region. Average temperatures globally vary between 27 degrees Celsius at the equator and -1 degree Celsius at the poles. Average precipitation varies from 2,000 millimeters per year near the equator to approximately 0 near the poles. Obviously, these two variations then have the potential to create very diverse climate zones across the planet. Breaking up the Earth's surface into zones based on temperature and precipitation, we see that the equatorial bands tends to be hot and wet. The subtropics tend to be hot/warm and dry, and the mid-latitudes vary between warm and cool, but remain relatively moist, depending on where you are on the continent. And the subpolar and polar regions are cold and dry. We can see what effect this has on the Earth's land surface, shown here in a NASA visible Earth image, where clouds have been digitally removed. Greener regions correspond to vegetation, requiring nominal levels of precipitation and warmth. Brown regions are the deserts of the world, generally found in the subtropics. White regions are covered in snow and ice and can be found in the subpolar and polar regions. Of course, the land surface varies throughout the year as seasons change. At the beginning of this animation, we see a cold and snowy northern hemisphere in January. The sun is in the southern hemisphere, and so precipitation is enhanced south of the equator. As we move throughout the season, the snows retreat and precipitation shifts northward. The edges of the deserts move with the rains. In the northern hemisphere summer, the Sahel region of Africa experiences the African monsoon, leading to its greening. Simultaneously, California becomes dry as the desert region edges move to the north. These shifts in the land surface are occurring within the context of a highly chaotic atmosphere. In this snapshot from a simulation of global weather patterns, we see sharp and spotty cloud patterns across the equator in the ITCZ associated with deep convection. Here, air is being violently drawn upward, leading to powerful rainstorms. We also see, in the subtropics here, a couple tropical cyclone events, looking like little spirals of clouds as they move across the domain. In the mid-latitudes, the most obvious cloud filaments are long and narrow. These are what are known as atmospheric river events that deliver moisture from the subtropics to the mid-latitudes. These are well-known features in California, both beneficial because they bring water to the state, but also potentially disastrous when they are extreme and cause flooding. Take a minute to watch the video at the link here and see more about how these clouds move depending on where you are on Earth. If you want to see more videos about the dynamic and chaotic nature of the Earth's system, here are some links showing both air movement in the atmosphere and in the oceans. These are very exciting and high-quality videos, and I strongly suggest you take the time in order to look. Okay, so now that we have a basic idea of how climate operates on the Earth, it's important to dig into the connectivity of the Earth system and understand how all the parts make a whole. The Earth system is in general made up of 5 natural parts: atmosphere, hydrosphere, which includes the water of the world, such as the oceans and the land surface water, the land and the land surface, which is the soil and the mountains and the topography, the cryosphere, which includes sea and land ice, as well as snow cover, and the biosphere, which is the ecosystems of the world, primarily referring to the vegetation of the world. At this point in our history, it's also indisputable that humans have now come to the point where we have a clear impact on the Earth. And because we are both connected to this system as well as influence this system, it is reasonable, I would say, to add humans as a 6th component of the Earth system. Thus, we usually talk about the coupled human-Earth system, which includes this new anthropogenic component. Diagrams such as this simplified model of the Earth system can help us understand how these components of the system are interconnected with one another. Processes within the Earth system, including precipitation, runoff, evaporation, ecology, winds, and waves, are responsible for building connections between the components of the Earth system. As a whole, the Earth system consists of numerous natural energy and moisture pathways. This is the Bretherton diagram, a simplified version of the connectivity that exists within the Earth system, both the physical and the geochemical system, as well as its external drivers on the left and human activities on the right. The Earth system is forced externally by the sun, through solar radiation, and from volcanoes, which affect the chemistry of the atmosphere. The energy from the sun is then distributed throughout the system through the aforementioned processes. Some of that energy goes towards driving the dynamics of the atmosphere, weather as we experience it. Some of that energy also moves ocean waters. Some goes into the biosphere and allows for the growth of animals and plants, and some of that energy evaporates water, allowing moisture from the hydrosphere to be carried over land. This whole system needs energy in order to operate. Humans influence the system not by changing how much energy is in the system, because that's essentially fixed by our solar inputs. However, we do change the pathways by which energy moves throughout the system. Through emission of greenhouse gases to the atmosphere, we can trap more energy near the surface and drive up surface temperatures, leading to more energy being stored in the land and ocean. Through land use change, we modify where energy is stored and how much of it is reflected by the surface. These modifications to the Earth system consist of a vast interconnected web of feedbacks that have an influence on every component in the system. The actions that we perform to modify the natural system feed back to us through what we refer to as climate change. Okay, that's enough for today. So what are we going to do for the next 3 months? Well, we're going to talk about our introduction to the Earth system. Next time, we're delving into understanding the Earth system and motivating why we want to understand the Earth system. We're going to talk about atmospheric structure, both vertical structure and horizontal structure, and then talk about paleoclimate, that is the history of the Earth and the Earth's atmosphere. We're going to then talk about global warming and answer the question, how do greenhouse gases impact temperatures? Then we're going to talk about water in the atmosphere. Water is inevitably a major component of these cycles of the Earth system. So we're going to ask, how does climate change impact the water cycle? Then we're going to talk about global impacts of climate change. In particular, we're going to talk about how climate change impacts extreme weather, how extreme weather even happens to begin with. We're going to talk about climate mitigation and adaptation, as well as social impacts from climate change. And then we're going to wrap things up. So that's all for today. Thank you very much for joining. As per usual, I'll be posting these asynchronous lectures a few days in advance of every course, so keep your eye out for the next lecture.